Okay, so the first problem is kinetic energy of the ejected electron, and let's read the problem and extract an information what's there in a form of the symbol. So ionization of a metal is shown, and something about photon and the wavelengths, and so we using this lambda as a wavelength, and that's a 23.7 nanometers. And then they said, well, we'll be able to transfer energy enough so to transfer the electrons, and all the energies coming to use for the electron to be ejected. So electron will be ejected from here. So the situation is very simple. If I shine the light, this is a metal, if I shine the light, this is an energy, and the electrons are bound to the atom, so it has a lower energy than the zero energy state. But if you put the energy down, they will start to come out, and eventually have an excess energy they will be used to move around. Okay? So this is a diagram I like to draw here. So other thing that you also refresh your memory is they are talking about kinetic energy. Okay, I got that. But single ejected electron versus moles of ejected electron. So this is a concept of what about the energy per one electron versus energy per moles of electron. And you remember the Avogadro's number? 6.022 10 to the 23. So actually unit is per mole, if I have to be exact. Okay. Anything that have this number we call Avogadro's number, and this is just like a baker's dozens, or if you have some kind of a unit to count the numbers, and this is the way that we count. We have 2 moles of gas means 2 times Avogadro's number of gas molecule in this room. So, so I'm going to kind of rewrite it. So, okay, so I read it once again. Ionization energy is 496 kilojoule per mole. And this is, remember, this is a per mole base, per Avogadro's number base. And this is something that will show up later. Okay? The lambda is 23.7 nanometers. And I would like to make a habit that 23.7 to the 10 to the minus 9 meters. So that I'm just dealing with a meter as a unit here. Okay? So this is information that I have. And then the concept, I think the probably cover in the lecture is the following. So I am going, why don't you draw this energy diagram with me. So this is an energy diagram. And there is an energy which is a 0 here. And you have a lot of energy state. This is an energy state that all the electron can have. And for certain electron, let's say their energy state is here. This is a 1 electron located here. This is a negative energy. This is a positive energy. And positive energy means they have a kinetic energy to move around. And what you do is you have a photon here, and which has a energy of h nu, and they going to hit this electron, and this electron will try to escape from the prison, and will show up going up all the way to up. Right? This is the same scenario that this is the electrons are not free electron because this is an atom, and they are bound to the nucleus, so they are not moving around. They are like a prisoner in this small atom shell, and if you shine the light, they will start to pump out the electrons. And if you have an extra energy, that's a kinetic energy. This is an energy required to ionize, so this is what we call the ionization. So can you start to make sense? You give an energy, some of the energy used for the prison break. The other one is I guess, to move around, right? So that's the one. So the natural equation that I can have is h nu is ionization energy plus kinetic energy. So that's an equation. And if I use this one diagram here, this is essentially what we call ionization energy. the energy to require to move the electron that is bound to the nucleus to the surface, to the zero energy. And then you have an extra energy that you put it in, that will be used as a kinetic energy. And these two together is essentially what we call energy that you injected over there. And that equation is trying to summarize what I showed in the diagram. Does it make sense? Yeah. Okay, so this is the first part. And then there is a little bit more calculation-driven component, because now I am going to remind you that we have to dealing with a single electron case and the moles of electron. So I want to show you be more clear understanding on this. This is an energy of photon, one photon. So what I can say is energy of photon is H. And then let me write a sort of the variance of that equation, which is a different color. If I say energy of 1 mole of photon, you know what will be a handy equation? You just multiply Avogadro's number to energy for a single photon. Right? So those are the two equations that you need to get used to it. And find my laser pointer. And if you start to looking at this equation, is a little confusing here. If you look at up there, ionization energy was given per mole base, right? So therefore, this one was, the ionization was given in a form of per mole base. So it is more like equation down here is more appropriate, right? So make sure that you kind of distinguish per particle base, per electron base, per mole base. So let's do this one by one. So first thing. So let's do the simple calculation. Energy for photon. That's a practice. That's an energy h nu, which is hc over lambda. And the lambda was given in the problem set. So, and the h was Planck constant, 6.63 10 to the minus 34. And I will say, remember, that's a unit. And then going back to the 1, and then I'm going to write multiply 3 times 10 to the 8 meter per second. This is a value that you guys use for your quiz number 2, speed of the light. And what was the wavelength of the light? And that was a 223.7 10 to the minus 9 meter. Okay? So that I can just use a meters and second and the joules, and then all MKS unit, and then you should be fine. And so if you're actually looking at the way that it is written, you can also check yourself, okay, the second per second is gone, meter is gone. All you have left is a joule, right? So you plug in those numbers, and you will get the answer in a unit of joule. So that's another good thing to check here. And that's the 8.39 10 to the minus 18 joule. I guess so it has no unit, but what this implying is for per 1 photon. Not photon. Photon. So that's a simple equation. And then I will also elaborate on this more. So this one is Avogadro's number times h nu. Right? So I calculated already the numbers there. So all I need to do is 6.02 to the the 10 to the 23. That's Avogadro's number, which is for your reminder, that's a per mole base. And then I am going to use the number up there, shown up here, 8.39 to the minus 18 joule. So if I multiply it together, then I will have something like 5.05 to the 6. And then you will have a unit called joule per mole. So they are different, right? The description is different, and then one is per mole base, and another one is actually do not say anything. That means one photon base. And sometimes the people like to change the joule into kilojoules. So that's 5.05 10 to the 3 kilojoule per mole. So I guess this is the unit, that's the unit for, okay. So let's go back to the problem that what was said here. The information, if you're looking at ionization energy, there was a per mole base. And I know I have to use the crucial equation that the energy that you put it in as in a form of a light will be used for the escaping the electron, and then extra energy is shown up as a kinetic energy to move the electrons around. Okay? You got that? So what was the question was a kinetic energy. So what is a kinetic energy? So number 2 is kinetic energy. So kinetic energy can be written as this: ionization energy. And there is a little bit, you have to be careful. And then I wanted to put an annotation here. This is a per particle in here for electron kinetic energy. And because of that, this kinetic energy that you are going to write, what you need is, you have this number up there, which is 8.39 10 to the minus 18 joule, right? And minus ionization energy. Ionization energy is 4.496 times 10 to the 3. That's a kilojoule. Joule per mole, right? So that's a kilojoule per mole. And then, if you're really looking at the unit, this one doesn't match. That's also, you can suspect that this is not a right, comparing apple to apple here. So therefore, what you need is, you need to divide that energy by Avogadro's number, which is per mole. And look at this. Nicely, they are gone now, right? And by doing so, only the joule term survive. And then the answer is here. 7.57 10 to the minus 18 joule. I guess that's a per 1 electron. And the per mole base electrons, the kinetic energy per mole, you want to introduce the Avogadro's number. So this is a sort of the variation of the kinetic energy, knowing that this IE value is per mole and KE value is per mole, right? Then I have to multiply H nu times the Avogadro's. So what you need to do is now, what was the number? Actually, I don't need to calculate it, it's already up there. So 5.05 and to the 3 kilojoule per mole minus 496 ionization energy. And then if you do that, sometimes I'll be careful when I deal with this number. 5050 minus 4 minus 6. You get 4.55 10 to the 3 kilojoules. Okay, so that's the answer for the second part. So let me recap this, and then we can move on to the next problem. Right? So look at that. The question is, what is the kinetic energy for a single ejected electron versus moles of electron? And the complication, the tricky part is your answers of ionization was given in a form of per mole basis, and you have to do kind of flip-flop per mole basis versus per particle basis. Any questions? Got this one done? Yeah. Oh, yeah, okay. And you know this answers key, actually the more wordy answer key is actually will be posted on the LMS, and then you guys can look at that. That's more descriptive than what you have. So you have a multiple means to kind of follow up the answer. So actually, let me show you this. This is actually an answer key that you guys can download it from the website. And I think that I will my poor handwriting, but I will always poor that I'll convert the PDF file. I'll put it on my own color version of answer key too. So you guys have all the multiple meaning, and on top, this is a video that I was hoping to provide it to you. So see how it goes.